Hi everyone, I am Dr. K. from the Department of Civil Engineering. It is my distinct pleasure to present our applications of finite element analysis in civil engineering. These sessions will illuminate how this powerful numerical techniques has revolutionized our capacity to model, analysis and design the complex structure that defines our modern built environment. Thank you for your engagement. To navigate our discussion effectively, we will progress through the structured outline. First, we will establish a foundational introduction to finite element analysis, defining its core principle. We will then explore the compelling need for the finite element method in modern engineering practice. This will followed by the explanation of the fundamental concept of discretization and the various types of finite element. We will objectively weight the advantages and limitations of this powerful tool. The core of our discussion will focus on the diverse and critical application of finite element analysis in civil engineering. We will then survey the landscape of software application, including ANSYS, Abacus, SAP 2000, and StatPro. Finally, we will conclude with a summary and glimpses into a practical case studies. Finite element analysis, or FEA, is not merely a software tool, it is profound numerical methodology for solving complex physical problems governed by differential equation across various domains, be it structural mechanics, heat transfer, fluid dynamics, or acoustics. It is elegant premise in one of divided the conquer. It subdivided a large, geometrically complex, and intellectually intimating the problem into a finer number of smaller or simpler or interconnected subdomains known as finite element. The solution is approximated within each element using interpolation function, and by enforcing compatibility and equilibrium at the connecting nodes, the behavior of the entire system is assembled and solved. This transformation intractable problem into manageable systems of algebraical equations. The adaptation of FEM was not a choice but a necessity driven by the limitation of classical analytical method. These traditional techniques are often powerless against complex geometries. How does one derive a closed form solutions for the stress distribution in a dam with a irregular cross section or a shell roof within double curvature? Classical method falter while finite element analysis thrives. Complicated loading. Real world structures are subjected to non uniform pressures, dynamic impacts, thermal gradient, and moving loads. Finite element method provides a framework to accurately simulate these complex problems into the natural scenarios. Realistic boundary conditions support in practice are never perfectly pinned or fixed. They involves practical fixity and elastic beating and complex soil structure interaction. All of this can be assembled incorporated into the FEA model. Furthermore, FEM addresses critical challenges that are paramount to modern design, material nonlinearity, real material behave inelastic, these yield, crack, creep, and string. Finite element method can model this sophisticated material model, moving beyond the simplistic linear elastic idealization. We no longer analyze structure and isolation. A pipeline experience thermal expansion and fluid pressure simultaneously. A building foundation interacts with the surrounding soil. Finite element method enables the coupled analysis of this multi-physics phenomena. Perhaps most importantly, FEA provides a detailed map of stress distribution revealing concentration zones that might be otherwise missed. They follow for optimized material efficient design that are both safe, economical, and eliminating costly over design. Discretization. The heart of finite element method is the process of discretization, the act of breaking down into a complex continuum into a finite simply mosaic for small, well-defined tiles. This is the step where we create a finite element. The points where these elements connected are nodes. The choice of element typically in crucial. One-dimensional element like beams and bars are used as a skeletal frameworks. Two-dimensional like triangles and quadrilateral model plates, shells, and plane stress and strain conditions. 3D models like tetrahedron, hexahedron are used for full solid modeling of massive structures like a dam and foundation. Let us crystallize the fundamental concepts notes. These are the fundamental points of the discretization model. They are locally where a degree of freedom, displacement, rotation, temperature are stored. They serve as the communication point between the elements, ensuring the compatibility. Um, these are the building blocks. Each element is the mathematical representation of a smaller part into a physical dominant, which has a specific shape, node configuration, and predefined formulation that describes how it behaves under load. The choice between a linear quadrilateral and a higher order element, for instance, has significantly implementation of the accuracy and computational cost. Degree of freedom. The concept of degree of freedom is centrally to understanding the size of and complexity of the final element problem. A degree of freedom is an independent physical quantity that defines that the state of the node. For example, a node in a 2D truss element has 2 degree of freedom, and a node of 2D beams element has 3 degree of freedom. A node in a general 3D solid element may have 3 translational degree of freedom. The total number of degree of freedom is a model determines the size of the global system of equation that must be solved. A larger complex problem can be easily have hundreds and thousands of and even millions of degree of freedom, underscoring the need for the computational problems. The advantages of finite element method are what make it the undisputed champion of modern numerical analysis. Versatility. It can handle virtually any geometry, material law, and boundary condition imaginably in engineering. Though missed refinement and use of the higher order element, it can capture localized effort like stress concentration with remarkable precision. The methodology in general and systematic from the model creation to solution and result extractions. It provides unparalleled visual insights into structural behavior through contour plots, animations, and detailed result graphs, transforming abstract number into intuitive engineering understanding. However, we must approach finite element analysis with a clear understanding and its limitations. Computational cost, high fidelity, 3D nonlinear and dynamic analysis can be demanded significantly computational resource and time. Creating a high quality mesh for complex geometries in the art in itself can be time consuming. A power mesh will lead to poor results. The software in an obedient calculator, not a validator. In accurate material properties, unrealistic constraints or improper loading will produce misleading yet often convincing the result. Interpreting result requires deep engineering to distinguish physical reality from the numerical outfit. The theory of finite element method is brought to the life through powerful commercial softwares. ANSYS, an industry behaves. ANSYS is a multi-physics platform renowned with its depth. It excels in advanced structural mechanics, computational fluids dynamics, CFD, with fluent, explicit dynamic and electromagnetic simulations along the study of coupled physics phenomena. A favorite in academia and industry pushing the boundaries of material and geometry nonlinearity, Abacus is exceptionally robust for problems involving complex contact, large deformations, fracture mechanics, and advanced material models like hyperelasticity and plasticity. Within a specific domain of engineering structure, two software packages are particularly dominant. SAP 2000. This is the comprehensive integrated software for the analysis and the design of structure of all kinds, buildings, bridges, dams, stadiums, towers. Its strength lies in its initiative interface, powerful analytical capability for both static and dynamic load, and its seamlessly integration with designing codes for concrete, steel, and aluminum. Next one is the StatPro, widely used for consulting films worldwide. StatPro is a versatile application for analyzing and designing visually any type of structure through the modular-based approach. It is celebrated for its extensive library of international design code and its efficiency in handling large scale projects.